A century ago, one of the smartest humans to ever do math scratched a tiny extra term into his universe. He added it to fix a problem that was not real, then later called it his biggest mistake. But here's the twist that still messes with physicists today. The universe seems to be behaving as if that mistake was right all along. Empty space may be packed with a strange pressure that is pushing everything apart faster and faster. If that is true, it decides how everything ends. So come with me into the weirdest scientific comeback story ever, and please like and subscribe. The reason this story hits so hard is that it starts with confidence. Real confidence. The kind that comes from watching your own ideas survive every attempt to kill them. In the early 20th century, Albert Einstein rewired physics so deeply that words like space and time stopped being background scenery and started acting like characters. When he finally wrote down his theory of gravity, the one we now call general relativity, it felt like the universe had been decoded. And then, almost immediately, his equations delivered a rude surprise. Einstein was not trying to build a drama. He was trying to write a clean description of reality. Matter tells space-time how to curve. Curved space-time tells matter how to move. That was the core idea. But when Einstein applied his new gravitational equations to the entire cosmos, they refused to sit still. A universe filled with matter should not remain frozen and eternal. It should either collapse inward under its own gravity or expand outward into the void. That was a problem. Not a mathematical error, a philosophical problem. At the time, most people assumed the universe was static, not because they had measured it, but because it felt natural. If the universe has always existed, then maybe it just sits there, unchanging, like a grand stage that never needs to move. Einstein shared that intuition, so when the math pushed back, he did something surprisingly human. He negotiated with the universe. In 1917, Einstein published a paper that added an extra term to his equations. That term acted like a kind of cosmic counterweight, a gentle repulsion that could balance gravity on the larger scales. It was tuned to hold the universe in place, neither collapsing nor expanding. This is what we now call the cosmological constant. It worked, on paper at least, but the moment you introduce a custom knob that can be dialed to get the result you want, you invite a dangerous question. Are you discovering reality, or are you decorating your beliefs with mathematics? Einstein's constant was elegant, and it seemed harmless, and it came from the right mind. That made it even more seductive. Then reality walked in with a telescope. In 1929, astronomer Edwin Hubble presented evidence that galaxies are moving away from us, and that more distant galaxies tend to recede faster. The universe was not static, it was expanding. And once you accept expansion, Einstein's carefully balanced cosmos becomes unnecessary. The equations did not need that extra term to keep the universe stable, because stability was never the truth to begin with. Einstein reportedly regretted adding the cosmological constant. The story is often told as a lesson in humility, even for geniuses. If you have a theory, let the universe tell you whether it is right. Do not force the universe to behave. For decades, that seemed like the end of it. The constant became a historical footnote, a little scar in the evolution of an otherwise triumphant theory. Scientists moved on to other mysteries, and there were many. The expanding universe raised new questions like where it began, how it evolved, and what it was made of. But the cosmological constant itself faded into the background, and that should have been that. Except the universe is not a polite narrator. It does not follow our story arcs. It does not care what we think is resolved. Near the end of the 20th century, astronomers were trying to answer a straightforward question. If the universe is expanding, then gravity should be slowing it down. Galaxies pull on each other. Matter attracts matter. The expansion should be decelerating, like a ball thrown upward that gradually loses speed. So scientists went looking for the slowdown. Instead, they found the opposite. In the late 1990s, observations of distant supernovae suggested that the expansion of the universe is accelerating. Not just continuing, but speeding up. Something was acting against gravity on the larger scales, and it was strong enough to dominate the future. The universe was not coasting, it was stepping on the gas. And suddenly, Einstein's discarded terms stopped looking like a relic and started looking like a clue. Because a cosmological constant does exactly that. It behaves like an energy built into space itself. As the universe expands, matter spreads out and thins, but a constant energy in empty space does not dilute in the same way. That means it becomes more important over time. In the early universe, matter dominates. Later, space dominates. And if space carries a kind of pressure that pushes outward, then acceleration is not just possible, it is inevitable. This is where the story turns from historical irony into a full-blown mystery. We now have a name for this mysterious driver of acceleration. We call it dark energy. That name is honest in the most unsettling way. It admits what we do not know. Dark energy is not a substance we can scoop up. It is not a faint gas hiding between galaxies. It is a behavior of the universe that we infer from measurements. The cosmos is expanding faster than gravity alone would allow, so something is doing work. Something is changing the fate of everything. And here is the part that should make your brain itch. If dark energy is just Einstein's cosmological constant, then it might be the energy of the vacuum, the energy of empty space. But when physicists try to estimate that energy using the rules of quantum physics, the result is wildly wrong. Not a little wrong, not off by a factor of 2. Wrong in a way that makes you question whether you're even using the right language to ask the question. So we are stuck in a strange place. The universe is accelerating. The simplest explanation looks like a term Einstein once called a blunder. But the physical meaning of that term is still a ghost. We can measure its effects, yet we cannot explain its identity. That is why this is not just a story about a genius making a mistake. It is a story about how science actually moves. It lurches, it doubles back. It finds a discarded idea in the trash and realizes it might be a missing puzzle piece. It is also a story about humility on a cosmic scale, because if we cannot explain what is driving the expansion of the universe, then we do not fully understand gravity, and we do not fully understand empty space, and we might not fully understand the rules that govern reality at all. Over the next 15 parts, we are going to trace the entire arc of this idea, from a quiet assumption about a static universe, to a mathematical patch, to an observational revolution, to a late-century shock that forced physicists to reopen a closed chapter. Along the way, we will meet the characters, the experiments, the stubborn clues, and the terrifying possibilities for how the universe ends. But first, we have to meet the young Einstein, not the icon on posters, the human being who learned to distrust common sense, and who accidentally set the stage for the biggest cosmic mystery of our time. Einstein did not begin as the official wizard of physics. He began as a young man with sharp edges, a stubborn dislike of authority, and a habit of staring at simple questions until they turned into monsters. For a while, he could not even land an academic job. So he took work at the Swiss patent office in Bern, reading technical applications all day, sorting out what was real invention and what was wishful thinking. It sounds like the opposite of a heroic origin story, but it mattered. The patent office forced him to live inside other people's machines. It trained him to ask very quietly what a device actually does, not what its inventor hopes it does. That mindset became a kind of superpower. When he looked at the universe, he treated it like a machine that had to make sense, one gear at a time. In 1905, while still working that day job, he unleashed a run of papers that would have made an entire department famous. For physics, it was like the sky cracked and new rules poured out. One paper tackled Brownian motion, the jittery dance of tiny particles suspended in a fluid. People had seen that motion for years and argued about its cause. Einstein treated it like a clue left by something too small to see. He showed that if matter is made of atoms and molecules, then their invisible collisions would jostle suspended particles in a predictable way. That was not just a clever explanation. It helped convince the scientific world that atoms were not metaphors, they were real. Another paper went after a problem with light itself. Experiments were showing something baffling about the photoelectric effect. Shine light on certain materials and electrons pop out. But the details did not match the old picture of light as a smooth wave that can deliver energy in any amount. Einstein proposed that light comes in discrete packets of energy. That idea later became one of the foundations of quantum physics. It also won him the Nobel Prize, not relativity, the weird light packet idea. And then came the papers that rewired space and time. Einstein asked an almost childish question. What would it look like to ride alongside a beam of light? If you could somehow keep up with it, would you see a frozen ripple hanging in space? That image felt possible to the human imagination, but it did not fit Maxwell's equations for electromagnetism, which implied that light always moves at the same speed in a vacuum. So Einstein made a decision that was both radical and clean. He trusted the math and the experiments, and he let common sense take the hit. He built special relativity on two simple principles. The laws of physics are the same for all observers moving at constant velocity, and the speed of light in a vacuum is the same for all such observers, no matter how fast they are moving. If you accept those two statements, the universe immediately becomes strange. Time stops being universal. Two people moving relative to each other do not agree on how long something takes. Length stops being absolute. Motion can shrink distances along the direction of travel. Events that seem simultaneous to one observer are not simultaneous to another. Space and time become interwoven, and what you call now depends on how you are moving. This was not a new gadget. It was a new reality. From this framework came the idea that mass and energy are two faces of the same underlying thing, that mass can be converted into energy, and energy can behave like mass. That insight is woven into nuclear physics, stars, and the deep accounting of how the universe stores and transforms energy. The point is not the famous formula people quote on posters. The point is the shift in worldview. Matter is not just stuff. It is a form of energy with a particular shape. Now pause and notice what this means for the cosmological constant story. Einstein's early triumphs did not come from collecting facts. They came from taking a small number of trusted observations like the behavior of light and the consistency of physical laws, and following them to their logical end, even when that end felt absurd. He did not win by being cautious. He won by being honest with the implications. That approach made him dangerous, in the best way. It also made him vulnerable, in a more subtle way. When you have repeatedly watched your reasoning outmaneuver the intuition of an entire era, you start to believe your intuition is special. You start to believe that when your inner picture of reality conflicts with the equations, maybe the equations need a little help. In 1905, Einstein learned that nature does not care what feels reasonable, it cares what is consistent. That lesson became his signature. But as we'll see, the same mind that was willing to let time itself bend and stretch still carried one old assumption like a precious heirloom, the assumption that the universe ought to be still. To understand why that assumption mattered, we need to watch Einstein take the next step. He had remade motion. Now he wanted to remake gravity, and that meant turning the universe from a stage into a living geometry. When most people hear the word gravity, they picture a force, something that reaches out across space and tugs on things. That picture is old, and it worked well enough for falling apples and orbiting planets. Isaac Newton gave it a precise mathematical form, and for more than 2 centuries it reigned without serious competition. The sun pulls on Earth. Earth pulls on you. End of story. Einstein suspected that this story was incomplete, not because it failed in everyday life, but because it did not fit comfortably with the new rules he had just written for space and time. Special relativity said that nothing, not even gravity, should send signals faster than the speed of light. Yet, in Newton's picture, if you moved the sun, Earth would feel the change instantly. Something was off. Einstein went hunting for a deeper description. His guiding idea was both simple and strange. Maybe gravity is not a force that lives in space. Maybe gravity is what happens when space and time themselves are curved. To build this idea, he leaned on an everyday experience. If you sit in a sealed elevator and it starts accelerating upward, you feel pressed into the floor. If you stand in an elevator that is not moving but is sitting on Earth, you also feel pressed into the floor. In both cases, your body feels a weight. Einstein took that resemblance seriously. He proposed that there is an equivalence between acceleration and gravity. Locally, you cannot tell the difference. From that seed grew a radical picture. Imagine space-time as a flexible fabric, not a literal sheet, but a 4-dimensional structure that can bend and ripple. Mass and energy tell this fabric how to curve. Once it is curved, the natural paths that objects follow are no longer straight in the usual sense. They're as straight as possible within the curved geometry. We call those paths geodesics. In this view, a planet orbiting a star is not being pulled around in a circle by an invisible force. It is falling freely along a straightest possible path in a warped space-time. A stone thrown upward is not fighting a downward tug. It is trying to continue in a straight line through a curved geometry, and the ground happens to interrupt. This way of thinking is harder to picture than arrows of force, but it heals the conflict with relativity. Changes in the distribution of mass and energy cannot update the shape of space-time infinitely fast. The curvature adjusts with a finite signal speed, the speed of light. Gravity becomes geometry, and geometry becomes dynamic. To make this precise, Einstein needed serious mathematical tools. He worked with tensor calculus, a language that can describe curvature in any number of dimensions. The result was the Einstein field equations of general relativity. They relate the content of the universe on one side, the energy and momentum, to the curvature of spacetime on the other. The test of any new theory is what it predicts that the old theory cannot. General relativity made several bold predictions. One of them was that light should bend when it passes near a massive object. If spacetime is curved, then even massless particles that follow straightest paths will have those paths deflected. Newtonian gravity can mimic this effect a little, but general relativity gave a specific quantitative prediction for how much starlight should shift when it grazes the sun. In 1919, during a solar eclipse, expeditions measured the apparent positions of stars whose light passed close to the sun. The results matched Einstein's theory more closely than the Newtonian expectation. Overnight, headlines announced that starlight bends and that Einstein had dethroned Newton. The world loves a dramatic story, and in this case the drama was real. Another prediction was gravitational time dilation. Time itself runs differently in different gravitational potentials. A clock deeper in a gravitational well ticks more slowly compared with a clock farther away. This sounds like philosophy until you realize that the global positioning system in your phone has to account for this effect. Satellites orbiting above Earth experience slightly weaker gravity and slightly different speeds, so their clocks drift relative to clocks on the ground. Engineers correct for general relativity every day so that your map app does not slowly go insane. The theory also implied the possibility of extreme objects where curvature becomes so strong that not even light can escape. We now call these black holes. When Einstein first wrote down his equations, he was not enthusiastic about these solutions. They felt like mathematical curiosities. A century later, we have seen the shadows of black holes and heard their collisions through gravitational waves, ripples in space-time that general relativity said should exist. It is hard to overstate how successful this theory has been. It does not just nibble at the edges of Newton's gravity. It replaces the conceptual core and then passes every precision test we throw at it. From the precession of Mercury's orbit to the signals from pulsars in tight binary systems, general relativity keeps saying the same thing. Gravity is geometry, and the geometry is alive. That success created an emotional trap. When a theory explains so much so well, scientists start to trust it almost like a law of nature rather than a model. They use it not just to interpret data, but to fill in places where data are missing. If your equations have carried you correctly through the wild hills of light and time, it is tempting to trust them completely when they speak about the shape of the universe. Einstein did exactly that. He pointed his new field equations at the cosmos as a whole and asked what kind of universe they describe. He assumed that on very large scales, matter is distributed roughly evenly. Homogeneous and isotropic is the technical way to say it. Same in every place, same in every direction. That assumption is reasonable if you average over enough galaxies. Then he solved the equations under those conditions. The answer was not what he wanted. The simplest solutions were not static. If you fill spacetime with matter and let general relativity run the show, the geometry tends to evolve. A universe can expand or contract. It does not like to sit perfectly balanced. Any small perturbation away from balance will grow. A slightly larger density here, a slight motion there, and soon you either have a universe that collapses inward or one that drifts apart. From the point of view of the equations, a calm eternal cosmos is not impossible, but it is delicately unstable, like a pencil balanced on its tip. The tiniest nudge sends it falling one way or the other. Einstein did not find that picture attractive. He had written the rules for a dynamic spacetime, Yet his imagination still held a picture of the universe as a quiet, timeless whole. The tension between what the math demanded and what his intuition preferred was now sitting in front of him in black ink. His solution was to change the equations. The cosmological constant was born as an extra term in the field equations that could counteract the natural tendency of gravity to make the universe collapse. It acted as a uniform energy density built into space itself, exerting a gentle repulsive influence on very large scales. By choosing its value carefully, Einstein could construct a universe that neither expanded nor contracted. With that tweak, general relativity once again seemed to describe a universe that matched his expectations. And for a brief moment, the story looked complete. Gravity had become geometry. Geometry had been tamed into a static cosmos, and the equations lay still on the page. But the universe, as we will see, had very different plans. For Einstein, the idea of a static universe was not a random taste. It felt like common sense for his time. Look up at the night sky without a telescope and what do you see? Stars that rise and set, constellations that shift slowly with the seasons, a pattern that seems ancient and unchanging. Philosophers had imagined eternal worlds for centuries. The cosmos was the stage, not the play. The stage did not move. When Einstein turned his new theory of gravity on this cosmic stage, he expected the equations to agree. They did not. A universe filled with matter and ruled by general relativity was restless by default. Gravity pulls. If there is no extra ingredient, that pull will make the universe either collapse inward or expand outward. A perfectly static universe was not the natural outcome. It was a knife edge. To see why, imagine a vast cloud of stars spread evenly through space. If the universe is truly static, every star must sit exactly in balance, feeling the tug of its neighbours but never drifting. Now give one region a tiny extra density. Slightly more matter, slightly stronger gravity. That region starts to pull in even more matter from its surroundings. The imbalance grows and the static picture falls apart. Einstein realised this instability. The mathematics made it unavoidable. A universe full of matter with no special extra term wants to evolve. And once you admit evolution, you invite the idea of a beginning, a history, and perhaps an end. At the time, that felt philosophically messy. It also felt unnecessary because no one had yet seen any sign that the cosmos as a whole was changing. So Einstein did something bold but very specific. He modified his own equations. He added a term that acted like a smooth energy density built into space itself. This term did not clump like matter. It did not gather into stars or galaxies. It stayed uniform everywhere. In the language of the field equations, it corresponded to a cosmological constant. In everyday words, it was a kind of pressure of the vacuum, a property of emptiness that pushed outward. The key feature of this constant was its sign. Ordinary matter pulls things together. This new ingredient pushed space-time outward, acting as a repulsive influence on large scales. By choosing its value with care, Einstein could make this repulsion balance the attractive pull of matter. Gravity tried to make the universe collapse. The constant pushed back. The result was a universe that hovered in a static state. On paper, the trick worked beautifully. The equations now allowed a static solution that looked stable enough to satisfy the imagination. The universe could be eternal, unchanging on the larger scales, with stars and galaxies perhaps forming and moving locally but with no overall expansion or contraction. Einstein was satisfied, at least intellectually. But there was a cost hidden in this satisfaction. The cosmological constant was not forced by any observation. No telescope had seen the universe expand or contract. Yet no telescope had seen it remain perfectly static either. The constant was inserted to protect a prior belief, not to explain a measured anomaly. It was a theoretical bandage. Most of the scientific community did not see this as a scandal. Their worldview matched Einstein's. A static universe felt natural. The constant was simply one more parameter, something that could be estimated once observations improved. In that sense, it did not feel any stranger than mass or charge. It was another number that physics would someday pin down. Still, the constant had an odd smell to it. It suggested that empty space itself carried energy. If you removed all matter and radiation, if you turned off every field you could name, the universe would not be truly empty. the vacuum would still have a built-in energy and a built-in effect on the geometry of space-time. At the time, there was no quantum field theory to make this idea feel familiar. There was no language of fluctuating fields and zero-point energies. Einstein's constant was a classical object, a smooth adjustment to the equation, not a collection of jittering quanta. That made it easier to ignore the question of what it really was. It could be treated as a bookkeeping device. While Einstein was smoothing his cosmos back into a static state, other minds were starting to poke at his equations in a different way. In the early 1920s, the Russian physicist Alexander Friedmann explored solutions to the field equations without insisting on a static universe. He kept the assumption that matter was spread out evenly on large scales, but he allowed the scale of space itself to change over time. The result was a family of dynamic models. Some universes expanded and then recollapsed, some expanded forever. In these models, the cosmological constant could play different roles. It could hasten collapse, slow it, or drive expansion. Einstein initially dismissed Friedmann's work, thinking it contained an error. When he later checked more carefully, he admitted that the math was correct. Still, he did not embrace the expanding universe picture. His intuition was rooted in stability. A few years later, Georges Lemaitre, a Belgian priest and physicist, independently derived similar expanding solutions and even connected them to observations of how galaxies seem to move away from us. He suggested that the universe might have started in a very dense, compact state and expanded from there. This was a radical thought in an era that preferred eternal sameness. There is a quiet irony here. General relativity, even with the cosmological constant, willingly described universes that evolve in time. It did not insist on the static case. It happily offered expanding and contracting options. The equations were more flexible than the imagination of their creator. Einstein's choice to fix his equations to get a static cosmos shows how powerful prior expectations can be, even for geniuses. He had invented a tool that wanted to tell him a wild story about a changing universe. Instead of listening, he tuned the tool until it repeated the calmer story he already believed. From one point of view, the cosmological constant looked like a stroke of genius. It made the theory fit a preferred picture and revealed that the equations could accommodate something like a uniform vacuum energy. From another point of view, it was a fine-tuning that pointed to a deeper misunderstanding. If you have to balance two huge effects with exquisite precision to keep the universe still, maybe the universe was never meant to be still at all. The cosmic stage was now set for a clash between mathematics and measurement. On paper, there existed static and dynamic cosmologies. In the mind of Einstein, the static version held the high ground. But telescopes were becoming more powerful, spectra were being recorded, distances to fuzzy spiral nebulae were being debated. Soon, new observations would force everyone, including Einstein, to stop asking what kind of universe they preferred and start asking what kind of universe they actually lived in. By the early 1900s, the universe looked small, not emotionally small but physically contained. Many astronomers believed that the Milky Way was the entire cosmos. Those faint fuzzy patches on old photographic plates, the spiral nebulae, were thought by some to be swirling clouds of gas inside our own galaxy. Others suspected they might be faraway island universes, full galaxies in their own right. This disagreement became famous as the Great Debate. People were arguing about whether the universe ended just beyond our stars or stretched far beyond anything we had yet imagined. The problem was simple to state and hard to solve. Distance. You can tell how bright something appears. That is easy. But to know how far away it is, you also need to know how bright it truly is. The universe does not come with labels. A nearby candle can look as bright as a distant star. If you misjudge the true brightness, you misjudge the distance. And if you misjudge the distance, your picture of the cosmos crumples. A breakthrough came from someone whose name did not become as famous as it deserved to be. Henrietta Swan Leavitt, working at the Harvard College Observatory, studied variable stars in the Small Magellanic Cloud, a nearby dwarf galaxy. She noticed a pattern in a class of stars now called Cepheid variables. These stars pulsate in brightness over regular periods. Leavitt found that the longer the period, the brighter the star truly is. This was the key. If you see a Cepheid and measure how fast it pulses, you can infer its true brightness. Then you compare that true brightness to how bright it appears, and use the inverse square law of light to work out how far away it is. Leavitt had created a new kind of cosmic yardstick. Years later, Edwin Hubble would use this yardstick to settle the Great Debate. Hubble was working at Mount Wilson Observatory in California, home to the Hooker telescope, which at that time was the most powerful optical telescope in the world. It had a mirror more than 2 meters across and could collect far more light than previous instruments. With it, Hubble took long exposure photographs of spiral nebulae, searching deep into their starry fields. In the 1920s, he found Cepheid variables in the Andromeda Nebula. He measured their periods, applied Leavitt's relation, and calculated their distances. The result was shocking. Andromeda was far outside the boundaries of the Milky Way. Not a gas cloud inside our galaxy, but a separate galaxy altogether. Once you accept that Andromeda is another galaxy, a simple thought follows. The night sky is not just filled with stars inside one giant disk. It is filled with galaxies scattered across a much larger cosmic landscape. The universe grows, not by a factor of 2 or 10, but by something closer to 1,000,000. Our home galaxy becomes one city among many, not the entire map. That alone would have rewritten cosmology. But Hubble was not finished. Astronomers had already noticed that spectra of many spiral nebulae showed a shift toward the red end of the spectrum. Light can be spread out into a rainbow, and dark absorption lines in that rainbow mark the fingerprints of specific elements. When those lines are shifted toward longer wavelengths, we say the light is redshifted. This can happen for several reasons. One is motion. If an object is moving away from you, its light is stretched, just as the pitch of a receding siren drops. Vesto Slipher, at Lowell Observatory, had spent years measuring these spectral shifts. He found that many spiral nebulae were strongly redshifted, meaning they were moving away from us, some at astonishing speeds. At the time, without reliable distances, it was hard to know what to make of this. Once Hubble began measuring distances to galaxies using Cepheids and other methods, he could combine his distance estimates with redshift data. When he did, a pattern emerged. The farther away a galaxy was, the greater its redshift, which meant the faster it was receding. Plot distance against recession speed, and the points line up in a rough straight line. From that line, you can read off a simple rule. On the largest scales, galaxies are moving away from one another in a systematic way. In every direction, distant galaxies recede faster than closer ones. This relation is now called Hubble's law. The interpretation that slowly took hold was not that we are sitting at the center of an explosion, with galaxies flying past us like shrapnel. It was that space itself is expanding. The fabric of the universe is stretching, carrying galaxies along with it. No matter where you stand, you see distant galaxies receding, and the farther away they are, the faster they appear to move. This picture matched the kind of dynamic solutions Friedmann and Lemaitre had already found in Einstein's equations. It also meant that the static universe Einstein had labored to build with his cosmological constant was not needed to match reality. When Einstein visited Mount Wilson and saw Hubble's results, the story goes that he admitted his error. He is often quoted as calling the cosmological constant his biggest blunder. Historians debate the exact phrasing, but the sentiment seems real. He had modified his theory to protect an assumption about the universe that turned out to be wrong. The cosmos was not sitting still, it was expanding. With a single set of distance and redshift measurements, the scale of the universe and its dynamic nature became undeniable. The cosmological constant, once added to hold the universe steady, seemed suddenly artificial. If expansion is real, you do not need a repulsive term to fight collapse into a static state, because there is no static state to preserve. For much of the 20th century, this was the narrative. Hubble had revealed an expanding universe. Cosmologists turned their attention to questions about the rate of expansion, the age of the universe, and the possibility of a hot, dense beginning. The cosmological constant faded into a background role, something you could set to 0 in the equations without guilt. But notice what had actually happened. Einstein's constant had not been disproven. Its original job had become unnecessary. There was no observational demand for a term that holds the universe in a static balance. So physicists chose the simpler option and dropped it. 0 felt cleaner than some arbitrary value. The real universe had given a clear answer about one question, whether it was static. It had not yet spoken about another, whether space itself carried a built-in energy. That second question would remain dormant for decades, waiting for a different kind of observation to bring it roaring back. For now, in the mid-20th century chapters of cosmology, the story looked tidy. General relativity described gravity. The universe was expanding. The cosmological constant was a curiosity in the history books, mostly mentioned as a warning about the danger of forcing your equations to match your preferences. It would not stay in the history books. Once the universe revealed that it was expanding, the cosmological constant lost its original reason to exist. It had been invented to hold a static cosmos in balance. If the cosmos had never been static, then the extra term looked like a clever answer to a question nobody should have asked. The natural response was to clean up the theory, sweep away the patch and restore the original lean form of Einstein's equations. Einstein himself led that cleanup. When he saw the evidence for expansion, he did not fight it for long. Whatever his personal preferences had been, he trusted data more than habit. The story that he called the cosmological constant, his biggest blunder, has become almost mythic. Whether or not those exact words were spoken, the emotion behind them fits. He had used his authority to nudge the universe toward a picture he liked. The universe refused to cooperate. Removing the constant was simple in principle. You just set its value to 0. The equation still worked, still curved space-time around matter and energy, still predicted bending light and time dilation and all the rest. The only thing that changed on paper was that there was no more built-in cosmic push. On the scale of the whole universe, gravity and matter were left alone to decide the story. For many physicists, this felt like an aesthetic victory. The theory became cleaner, one less arbitrary parameter to explain. The expansion of the universe could be understood as momentum left over from an earlier state, gently slowed by gravity depending on how much matter and energy the universe contained. In this view, the future came down to a single contest. Expansion trying to carry galaxies apart, gravity trying to pull them back together. Inside this cleaner framework, cosmologists built models where the universe might eventually recollapse into a big crunch, or expand forever but at an ever-decreasing rate, or hover near a critical balance where expansion slows but never quite reverses. Each option depended on the density of matter and radiation. The cosmological constant was no longer part of the mainstream conversation. You could mention it, but most people were happy to treat it as a lesson from history, not a live ingredient. In textbooks, the term survived as a symbol and a cautionary tale. You might see the field equations written with a placeholder for the constant, followed by the reassuring line that current observations are consistent with setting it to 0. Students learned that Einstein had once introduced this term for a static universe, and that later evidence made it unnecessary. The moral was clear. Do not bend a successful theory to match a favorite picture of reality. Let reality do the bending. Beneath that moral sat a deeper question about what counts as a mistake in science. On one level, Einstein had indeed made an error. He let his belief in a static cosmos guide a modification to his equations before the universe had earned that belief. He trusted intuition over prediction. He tuned a parameter to get the answer he wanted. That is exactly the sort of thing physicists warn each other about in coffee room conversations. On another level, the story is less simple. The cosmological constant was not nonsense scribbled in haste. It was a mathematically legitimate term that general relativity naturally allows. The equations do not forbid an energy built into empty space. They quietly invite it. In that sense, Einstein had stumbled onto a possibility that would later become central. He just gave it the wrong job description. This is where mathematics shows its double nature. Equations can hint at things before anyone knows how to test them. They can also tempt you into adding features because they are allowed, not because they are needed. A term that fits elegantly into a formula can be either a profound insight or an elegant distraction. Without data, you cannot tell which. In the mid-20th century, the community decided that the constant was an elegant distraction. Simpler was better. The expanding universe had plenty of puzzles already. Astronomers were trying to measure its age, its curvature, its contents. They were grappling with the idea of a hot, dense early phase that would later be called the Big Bang. They were building the distance ladder, mapping clusters of galaxies and hunting for the cosmic microwave background. It was easier to do that work in a universe where space did not have extra built-in energy. Yet the constant never vanished completely. A few theorists pointed out that keeping it non-zero could help with certain tensions, like the age of the universe inferred from expansion compared with the ages of the oldest stars. Others explored cosmological models where a small positive constant changed the long-term behavior of expansion. These ideas lived in the margins. They were interesting but not urgent. The data did not demand them. The deeper irony is that even as the constant faded from attention, quantum theory was quietly making the idea of energy in empty space seem less strange. Quantum fields do not sit perfectly still. Even in their lowest energy state, they flicker with virtual activity. That suggests that the vacuum itself might carry energy. And if the vacuum carries energy, general relativity says it should gravitate. In other words, it should act like something very much like a cosmological constant. This potential connection between quantum fluctuations and the constant was noticed, but again it did not feel urgent. The calculations gave absurd answers, and the observational side of cosmology was not yet precise enough to see whether there really was any sign of such a vacuum energy in the large-scale behavior of the universe. So the topic remained more of a curiosity in theoretical discussions than a driver of research. Looking back, the silence around the cosmological constant in those decades is almost eerie. Hints were there. The mathematics allowed it. Quantum theory hinted at it. Some models used it. But without a clear, measurable effect, it stayed in the attic of cosmology, boxed up with other odd ideas. Science often works that way. A concept can exist for years as a side note, waiting for technology and data to catch up. A single parameter can move from irrelevant to central in one experimental generation. The cosmological constant was quietly biding its time. Einstein's regret, real or exaggerated in retelling, became part of the culture. Young physicists learned to respect observation, to be wary of tuning knobs just to make things pretty, to remember that even giants can lean too hard on their gut feeling. The constant turned into an example of what not to do. The universe, however, had already decided that it would need that term for a completely different reason. At the end of the 20th century, astronomers would turn their best instruments on some of the brightest explosions in the cosmos, not to resurrect Einstein's abandoned constant, but to answer a much more modest question about how fast expansion was slowing down. The answer they found would drag the cosmological constant out of the attic and drop it back into the center of the room. When people hear that the universe is expanding, most picture something very human. A firework going off, a bomb in empty space. A point at the center where everything blew apart and galaxies racing away into the dark. It is a vivid picture. It is also wrong. The real expansion is stranger and in a quiet way much more beautiful. To get it right, we have to ask a careful question. When we say the universe is expanding, what exactly is getting bigger? It is not the galaxies themselves. Inside a galaxy, stars orbit under the pull of gravity. Their motions are set by the dance between mass and the curved space-time that holds them together. That structure is tight enough that the gentle stretching of the universe as a whole barely matters. The same is true on smaller scales. Planets do not drift away from their stars because of cosmic expansion. Atoms do not slowly swell. Your chair is not being pulled apart by the growth of space. What is expanding is the distance between large structures that are not bound together. Imagine galaxies as dots on a stretchy rubber sheet. The sheet itself is space. When you pull the sheet, the dots move apart, not because they're sliding over the surface, but because the surface is stretching between them. From the point of view of any one dot, it looks as if all the others are moving away. This is where the famous balloon picture comes in. Put dots on the surface of a balloon, then blow it up. As the balloon expands, every dot sees every other dot receding. There is no special center on the surface. The center is somewhere in a higher dimension that the ants living on the balloon skin cannot access. In a similar way, in our three-dimensional universe, there is no privileged center of expansion. Wherever you stand, far enough away, galaxies are receding. That is a hard idea to digest because our brains are built for local experiences. In daily life, expansion means something grows into something else, a cloud into the sky, an explosion into the surrounding air. There is always an outside. The universe does not seem to have an outside. Space is not expanding into a larger emptiness. It is simply changing its own scale. This difference matters because it changes how we think about the beginning. If you rewind the film of expansion, distances shrink. Galaxies draw closer. Clusters crowd together. The average density increases. Keep running the film backward and you reach a time when everything was much hotter and much more compressed than it is now. Run far enough back and you approach a state where the density and temperature are beyond anything we can probe directly. That early phase is what people loosely call the Big Bang. The name is misleading. It suggests a local event in space, a blast with a center, a moment when something exploded into nothing. The modern view is quieter and stranger. The early universe was hot and dense everywhere. It did not explode into space. It was space, in a different state, evolving. When astronomers in the mid-20th century started to take expansion seriously, they realized that it pointed to a finite age. If you know how fast the universe is growing today, and you have some idea of how that rate has changed, you can estimate how long it has been since everything was close together. That gives a rough age of the universe. This idea made some physicists uneasy. A universe with a beginning feels philosophically loaded. It invites questions that physics does not know how to handle. Why then? Why that way? Others saw it as an exciting clue. If the universe had an early hot phase, maybe traces of that time still linger. Maybe there are fossils of the beginning written in radiation and in the arrangement of galaxies. The expansion is not just a curiosity, it is a bridge between the present and that early state. Another subtle point is that expansion does not mean everything moves away from everything with the same speed. The Hubble relation tells us that on very large scales, recession speed is roughly proportional to distance. Double the distance, roughly double the apparent speed. But superimposed on this smooth pattern are local motions. Galaxies in the same cluster orbit one another. Gravity pulls nearby structures together even while the overall fabric stretches. You can think of it like this. Imagine a loaf of rising raisin bread. The dough is space. The raisins are galaxies. As the dough rises, the raisins drift apart. A raisin twice as far from you in the dough moves away twice as fast. That is the large-scale expansion. At the same time, individual raisins might wiggle a little as the dough pushes on them. That is local motion. Gravity plays the role of the dough's stickiness, keeping some raisins in clumps. In this picture, expansion is not something that turns on and off. It is a feature of the entire solution of Einstein's equations. Once the universe is expanding, you cannot simply wish it into a static state. The expansion rate can change. It can slow down under the pull of gravity. It can in principle even reverse in certain models, leading to a recollapse. But it does not just halt without cause. For most of the 20th century, cosmologists expected gravity to be slowing the expansion. Matter attracts matter. On cosmic scales, all the galaxies pull on one another. Over billions of years, that pull should act like a brake. The big question was how strong the brake was. Was there enough matter to eventually stop the expansion and bring everything back together, or too little, leaving the universe to coast forever? Notice what is missing from this picture. There is no built-in push. Once the cosmological constant was set to 0 in the mainstream models, nothing in the equations was giving the universe an extra shove outward. Expansion was an initial condition, not an ongoing engine. That made the next step seem straightforward. If you can measure how fast the expansion is slowing, you can infer how much matter the universe contains. You can weigh the cosmos by watching it breathe. On paper, this was an elegant plan. The expansion itself had already told scientists that the universe has a history. They now wanted to use that history to map its contents and predict its fate. Would it expand forever, cool and fade into a thin soup of lonely galaxies? Would it someday reverse and end in a catastrophic crunch? Would it hover near a delicate balance between the two? To answer that, astronomers needed a tool that could reach far back in time, to see how the expansion behaved when the universe was younger. That meant finding objects bright enough to be seen across billions of light years and regular enough to serve as standard beacons. Those objects turned out to be among the most violent events in the universe, special kinds of stellar explosions whose brilliance can briefly rival an entire galaxy. They would become the rulers with which we measure not just distance, but the bending of time itself on the largest stage imaginable. Measuring the universe sounds majestic, but in practice it starts with a very human problem. You look up, you see a bright dot, and you have to ask the most basic question in science. How far away is that thing? Almost everything else in cosmology depends on the answer. To know how fast something is moving away, you need both its velocity and its distance. Redshifts gave astronomers a handle on velocity. Distance was the nightmare. Nearby there is a simple method: parallax. As Earth orbits the Sun, a nearby star appears to shift slightly against the background of more distant stars. Measure that tiny shift, and with some basic geometry you can calculate the distance. It is a beautiful technique, but it dies quickly with distance. For faraway stars and galaxies, the apparent shift is too small to see, even with the best instruments of the mid-20th century. So astronomers built a distance ladder. Each rung uses a method that works out to some range, then hands off to another method that works farther but must be calibrated using the first. Parallax calibrates certain bright stars. Those stars calibrate clusters. Clusters calibrate galaxies. Each step introduces uncertainty. If you get the lower rungs slightly wrong, the errors can grow as you climb. Henrietta Leavitt's Cepheid variables became one of the most important rungs. Because their pulsation period is tied to their true luminosity, they serve as cosmic yardsticks. By the late 20th century, observatories including the Hubble Space Telescope were using Cepheids to refine distances to nearby galaxies with impressive precision. That anchored the base of the ladder. But to test how the expansion of the universe changes over time, you need to reach much farther out, to galaxies so distant that their light has been travelling for billions of years. You want to see the universe as it was when it was young, then compare that view to the universe today. It is like looking at childhood photographs of the cosmos and asking how its growth has changed. For this, astronomers needed something far brighter than ordinary stars. They needed fireworks that could be seen halfway across the visible universe. Nature, conveniently, provides such fireworks. Some stars end their lives in catastrophic explosions called supernovae. In a fraction of a second, a supernova can outshine the entire galaxy that hosts it. There are different types of supernova, but one in particular, called Type Ia, turned out to be extremely useful. A Type Ia supernova usually forms in a binary system. A dense stellar remnant, a white dwarf, steals matter from a companion star. As it grows, it creeps toward a critical mass. Past that threshold, and the white dwarf can no longer support its own weight. Carbon and oxygen in its core ignite in a runaway thermonuclear reaction. The star is torn apart in an almost perfectly violent way. Because the conditions for this catastrophe are similar from one white dwarf to another, these explosions reach nearly the same peak luminosity. They are not perfectly identical, but they are close enough that with some corrections based on how quickly their brightness declines, you can treat them as standard candles. Measure how bright a Type Ia supernova appears, adjust for its light curve, and you can infer how far away it is. This is the supernova trick. The universe throws you a flashbulb of nearly known power. You read its apparent brightness, apply your calibrations, and get distance. At the same time, you can measure the redshift of the galaxy that hosted the supernova by splitting its light into a spectrum and checking how the familiar lines of elements have been stretched. Put these together, and each distant supernova becomes a data point. It tells you how fast the universe was expanding when that light was emitted, and how far away that event is now. Collect many such points at different distances, and you can reconstruct how the expansion has changed over billions of years. In the 1990s, two major teams set out to do exactly this: the Supernova Cosmology Project and the High Redshift Supernova Search Team. Their goals were not to discover something exotic. Their goals were almost modest. Measure the deceleration of the universe. Use that deceleration to figure out how much matter it contains. The logic was straightforward. In a universe without a cosmological constant, gravity is the only large-scale player. Matter pulls on matter. Over time, that pull should slow the expansion. The more matter there is, the stronger the slowdown. If you can measure how expansion has changed, you can infer the density of matter. That is the cosmic break test. On the blackboard, the expectations were neat. If the universe is full of matter, then very distant supernovae, whose light left them when the universe was younger, should not be as far away as they would be in a universe that has been expanding freely at the same rate all along. The early expansion should have been faster, then slowed. That would leave a signature in the distance-brightness relation. Distant supernovae should appear a bit brighter than they would in a universe with no slowdown, because they would be slightly closer than in that comparison case. The teams were careful. They knew that supernovae are messy astrophysical events. Dust can dim light. Local environments can introduce noise. They had to select clean examples, correct for known effects, and compare results from different telescopes and instruments. This was not just a matter of drawing a straight line on a graph. It was a delicate statistical ballet. Still, the overall plan had a comforting clarity. Take a well-tested theory, general relativity without a cosmological constant. Add a reasonable assumption that gravity should slow expansion. Build a clever experiment using supernovae as candles. Then read off the amount of matter in the universe from the pattern you see. In many ways, it was an experiment designed to confirm expectations, not to overturn them. There is a psychological pattern here that repeats across science. When a theory is as successful as general relativity had been, and when you have already removed an awkward term that once felt artificial, you do not go into a measurement expecting a revolution. You go in expecting to sharpen the numbers, reduce uncertainties, and bring the theoretical and observational pictures into tighter agreement. Behind the scenes, there were still questions. Different measurements of the Hubble constant, the current expansion rate, did not quite agree. Estimates of the age of the universe based on that rate sometimes conflicted with estimates of the ages of the oldest known star clusters. The cosmic bookkeeping did not balance perfectly. But these looked like technical issues, not cracks in the foundation. Supernova cosmology was supposed to be one more instrument in the orchestra, another way to constrain parameters. No one was designing it as a test of whether the universe might be doing something radically unexpected. Yet hidden in the light curves of those distant explosions was a message. To hear it, astronomers had to trust their calibrations, check their biases, and be willing, as Einstein had once been, to let the equations tell them something uncomfortable. They had set out to measure deceleration. What they were about to find was that the universe is not slowing down at all, it is speeding up. When the supernova teams finally began to collect enough distant explosions, they were nervous in a familiar way. Not terrified, not expecting a revolution, just the tension that comes when years of careful work are about to congeal into a line on a graph. In their minds, the likely outcome was straightforward. The universe should be expanding, but with the expansion gently slowing under the pull of gravity. The data would show that slowdown. From that curve, they would estimate how much matter the cosmos contains. They plotted the points, and the universe quietly refused to play along. Each distant type wire supernova came with two key numbers. Its redshift, which told them how much the universe had expanded since the light was emitted, and its apparent brightness, which told them, after calibration, how far away it is now. When they placed these points on a diagram and compared them to the expectations for a decelerating universe, something strange happened. The supernovae were too dim. Distant explosions, ones whose light had been travelling toward us for billions of years, appeared fainter than they should have been if the expansion had simply been slowing down under gravity alone. Fainter meant farther. Farther than any decelerating model without a cosmological constant would allow. There were many moments of doubt. Dimmer can also mean dustier. Perhaps there was some subtle grey dust between galaxies that was absorbing light without leaving strong fingerprints in the spectra. Perhaps the distant supernovae were intrinsically different from nearby ones in some way that had escaped notice. Perhaps the calibrations were off. Perhaps, in short, the candles were not as standard as everyone hoped. The teams attacked these possibilities with a kind of relentless paranoia. They checked for signs of unusual dust. They separated supernovae by type of host galaxy to see if environment mattered. They compared different analysis methods. They worried about selection effects, about the simple fact that it is easier to detect brighter supernovae at great distances, which can bias samples. Yet as the data grew, the pattern remained. In every careful comparison, the distant supernova stubbornly preferred a universe that was not slowing much at all. In fact, the best fit model suggested that the expansion had been slower in the past and was faster now. Instead of gravity acting as a brake, something was behaving like a cosmic accelerator. On the graph, that difference shows up as a gentle but unmistakable bend in the distance curve. Instead of sitting on the track for a decelerating universe, the points drift onto a track that corresponds to a universe whose expansion rate has begun to speed up. It is not a dramatic corner, it is a subtle curve, but subtle curves can carry enormous meaning. There was a moment, different for each researcher, when the implications clicked. If the universe is accelerating, then either general relativity breaks down on large scales, or there is another ingredient in the cosmic energy budget that has so far gone unseen. Something that behaves not like matter, which clumps and decelerates, but like a smooth energy spread through space which can push. That second option sounded hauntingly familiar. In the language of Einstein's equations, you can describe this new ingredient in many ways. You can treat it as a fluid with negative pressure. You can treat it as a property of the vacuum, or you can write it as a simple cosmological constant term, the same symbol that had been set to zero in so many textbooks. What mattered for the supernova data was not the philosophical label. What mattered was how this stuff affects expansion. A positive cosmological constant acts as a kind of repulsive gravity. It does not fight attraction directly on small scales, where matter dominates and structures form, but on the larger scales it drives acceleration. As the universe grows and matter thins out, the constant term becomes increasingly important. There comes a time when it wins. The supernova results pointed straight at that scenario. Both major teams, working independently, found that the best fit to their data was a universe with a substantial positive cosmological constant. Not enormous, but not zero. Enough to dominate the energy budget today. Enough to account for the observation that the expansion is currently speeding up rather than slowing down. The reaction in the community was a blend of disbelief and reluctant excitement. The return of the discarded term felt almost like a joke from the universe. Einstein's biggest mistake, the patch he'd introduced for the wrong reason and then publicly regretted, seemed to describe a real feature of cosmic history. At first, some tried to interpret the results in more conservative ways. Perhaps the data were not yet decisive. Perhaps other measurements would pull the answer back toward a purely matter-dominated cosmos. But then other lines of evidence began to point in the same direction. Maps of the cosmic microwave background, the faint afterglow of the hot early universe, carry information about the geometry and content of the cosmos. Measurements of galaxy clustering and large-scale structure reveal how matter has grown under gravity over billions of years. When cosmologists started to fit models to all these different observations at once, the same picture rose to the top. A universe in which roughly 2/3 of the total energy density resides in a smooth component that does not clump and that drives acceleration. A smaller fraction in dark matter, which clumps and shapes galaxies but does not emit light. An even smaller fraction in ordinary matter, the stuff of stars and planets and people. In that accounting, the cosmological constant is no longer a footnote, it is the main term. The name dark energy emerged as a kind of honest placeholder. It is dark because it does not shine or absorb light in any direct way we can see. It is energy because in the equations it behaves like an energy density with unusual pressure, one that pushes rather than pulls on cosmic scales. Beyond that, the name admits ignorance. We do not yet know what it is. This was the curveball. For decades, cosmologists had imagined that the central question was how much matter the universe contains, and whether that matter would eventually slow expansion to a stop. The supernova data reframed the question entirely. The dominant component is not matter at all, but something more elusive. The real fate of the universe depends on the properties of this dark energy. There is a deeper discomfort hiding here. The cosmological constant is, mathematically speaking, the simplest way to describe dark energy. It is just a number. Once you include it, the theory remains elegant and predictive. It fits the data remarkably well, but the simplicity is almost too perfect. It tempts us to accept a symbol in place of an explanation, because a constant term in the equations answers the how without answering the why. Why does the vacuum have this particular energy density and not another? Why is its value so small compared with the naive expectations of quantum field theory, yet so large that it dominates the universe today? Why did it become important at roughly the same cosmic epoch when galaxies and stars and life emerge? These questions turn the supernova discovery into more than a technical refinement. They turn it into a crisis of understanding. The universe is accelerating. The simplest way to model that acceleration goes by the name of a constant Einstein once called a mistake. But the real identity of dark energy remains hidden. We have the shape of the curve. We need the story behind it. In the next part, we will watch that constant step fully back into the spotlight, not as a historical patch, but as the leading suspect in the mystery of why the universe will not stop speeding up. When the dust settled from the supernova shock, cosmologists were left staring at a simple truth. The universe was accelerating, and the easiest way to describe that acceleration was to bring back the very term that had once been thrown away. Einstein's cosmological constant stepped out of the historical footnote and into the main equations again, not as a nostalgic curiosity, but as the leading explanation for what dark energy might be. To feel why it fits so naturally, we have to look at how different ingredients in the universe behave as it expands. Imagine you double the size of the universe. Distances between unbound galaxies increase. The volume of space grows. What happens to matter? Take a fixed number of particles and spread them over a larger volume. Their density drops. The same is true for radiation, the background light that fills space. As the universe grows, photons are stretched to longer wavelengths. So not only are there fewer per unit volume, each carries less energy. Both matter and radiation dilute as the cosmos stretches. Now picture an energy that does not dilute, an energy that lives not in particles, but in space itself. If every cubic meter of vacuum has the same tiny amount of energy, then when the universe expands and creates more cubic meters, the total amount of this energy increases. Its density stays constant. That is what a cosmological constant does in the equations. It behaves like a uniform energy of the vacuum present everywhere, with the same value at every point unaffected by expansion. Early on, when the universe was much smaller and denser, matter and radiation dominated. Their energy densities were huge compared with any plausible constant background. But as space grew and matter thinned out, the ratio shifted. Matter kept fading. The constant did not. Eventually, there came a time when this vacuum energy, if it existed, would overtake matter and become the main driver of cosmic dynamics. The supernova data suggested that we live after that takeover. Once a cosmological constant dominates, its effect on expansion is dramatic. The gravitational pull of matter still tries to slow things down, but the constant acts as a kind of negative pressure that pushes on space-time. The result is not just continued expansion, but accelerated expansion. The scale factor, the parameter that describes how distances grow, begins to increase faster and faster. This matches what the supernova team saw. The universe had spent much of its history slowing under the influence of matter, then more recently entered an accelerating phase as dark energy took over. A positive cosmological constant slots into this story without strain. It is exactly the kind of ingredient that would do this. Better yet, once you admit this term, a whole suite of observations line up. Maps of the cosmic microwave background show patterns of hot and cold spots that depend on the geometry of space and on how different components of the universe have tugged on each other over time. When scientists fit models to those patterns, they find that the overall geometry looks very nearly flat, in a technical sense, but the matter content alone is not enough to make it so. A cosmological constant supplies the missing energy density, preserving flatness while allowing matter to remain at the level inferred from galaxy clusters and other measurements. Large-scale surveys that chart the distribution of galaxies also support this picture. The way structures have grown, from tiny fluctuations in the early universe to the web of clusters and filaments we see today, depends on the competition between gravitational attraction and cosmic expansion. In a universe with only matter, structure growth would follow one pattern. In a universe where a cosmological constant becomes dominant at later times, growth slows as expansion speeds up. Data from galaxy clustering, gravitational lensing, and other probes point toward that second story. Put all of this together, and the best fit model has a simple form: general relativity with a non-zero cosmological constant. A universe that is mostly dark energy by energy budget. with the rest split between dark matter and ordinary matter. This framework is sometimes called the standard model of cosmology. At its mathematical core sits the term Einstein once regretted. There is a kind of haunting elegance in this. The cosmological constant does not require new dynamical fields. It does not require the equations themselves to be modified. It is a single number added to a theory we already know works incredibly well in many other contexts. With that one number, you can account for acceleration, preserve the successes of general relativity, and match an array of observations. In physics, simplicity is seductive. When a minimal extension of a trusted theory suddenly explains a flood of new data, the temptation is to declare victory. We have a parameter that fits. We understand the expansion. The story is over. But the universe is rarely that kind. The constant is a perfect descriptive tool. It tells us how space-time curves given a certain vacuum energy. What it does not tell us is where that energy comes from, why it has the value we measure, or whether it is truly constant in time. Here is where quantum theory tries to join the conversation and immediately makes it worse. In quantum field theory, even empty space is seething. Fields fluctuate. Virtual particles bubble in and out of existence. When you calculate the energy of this vacuum activity in a naive way, you get an enormous value, many orders of magnitude larger than the tiny dark energy density inferred from cosmology. If you interpret the cosmological constant as vacuum energy, you run straight into one of the most embarrassing mismatches between theory and observation in physics. One option is to imagine that there is some unknown mechanism that cancels almost all of this quantum vacuum energy, leaving behind only a tiny residue. Another is to suspect that we are computing the wrong thing, that our understanding of vacuum in quantum field theory is incomplete when gravity is included. Either way, the cosmological constant becomes a clue that our deep theories are missing something. There is another layer of unease. The value of the constant is small but not zero. If it were much larger, cosmic history would look very different. Too large, and acceleration would begin so early that matter would never clump into galaxies and stars. Too negative, and the universe would collapse quickly. The observed value sits in a narrow band that allows complex structures and, eventually, beings like us to exist. This coincidence has inspired ideas about selection effects and multiverses, speculations in which different regions of a larger reality might have different values, and we simply find ourselves in a patch where the constant is small because only such patches can host observers. These are intriguing possibilities, but they move us far beyond the original neatness of a single number in an equation. So we are left with an odd tension. On one hand, a non-zero cosmological constant fits the data with almost suspicious ease. On the other hand, we have no widely accepted explanation for its origin or its value. We can write the term. We can measure the number. We cannot yet explain it in a satisfying way. Einstein's discarded term has come back with a vengeance, not as a mistake to be erased, but as a reminder that the universe can use even our errors as stepping stones toward deeper puzzles. The constant he once tuned to hold a static cosmos now describes a dynamic vacuum that is tearing galaxies apart from one another on the larger scales. The story has flipped. Instead of being the patch that kept the universe still, the cosmological constant has become the engine of its runaway future. In the next part, we will dive into the most painful part of this story, the place where our neat ideas about vacuum energy smash into the brute fact of the measured value. It is where numbers stop being friendly and start screaming that something in our understanding must change. If dark energy is real, and if it really behaves like a cosmological constant, then a brutal question lands on the table. Where does it come from? Empty space is not supposed to be lazy. In quantum theory, even nothing cannot sit still. The vacuum is a restless sea of fields, constantly twitching, constantly borrowing and repaying energy on scales too small for us to see directly. All that activity should add up to something. The cruel part is that when we try to calculate that something, we get an answer that is catastrophically wrong. To see the shape of the problem, imagine you are a quantum field theorist trying to be honest. Every kind of particle you know, every field that fills space, contributes a little bit of energy even in its lowest state. You carefully add up those contributions. You let the fields vibrate up to some very high frequency, not quite to infinity, but to a natural cutoff where you expect your theory to stop making sense. Then you look at the total. The number that comes out is enormous, not just big in an everyday way. big in a way that dwarfs every cosmic quantity you're used to. When you compare that predicted vacuum energy to the tiny dark energy density that cosmology measures, the ratio is staggering. Depending on how you count, you can get an overshoot of around 1 followed by 120 zeros. In physics, factor of 2 disagreements can be blamed on rounding. Factor of 10 disagreements can be blamed on missing details. A mismatch of 10 raised to the power of 120 is not a detail, it is a scream. This is why people sometimes call it the worst prediction in physics. Not because the math was sloppy, but because the calculation followed the rules of a theory that works incredibly well in particle physics, only to smash into the quiet fact that the universe is not exploding. If the vacuum energy were really as large as that naive sum suggests, space-time would curl up into something unrecognizable. Galaxies, stars, chemistry, none of it would exist. So we seem to have two clashing truths. Quantum fields insist that empty space should be stuffed with energy. Cosmological measurements insist that if there is vacuum energy, it is tiny. And yet that tiny value is large enough to dominate the current expansion of the universe. Too small for particle physics, too big for comfort, just right to control the future. Faced with this, physicists have tried several lines of escape. One idea is that there is some deep principle that forces all those contributions from different fields to almost cancel. Perhaps there is a symmetry of nature that demands the vacuum energy be exactly zero. For a while, a hypothetical symmetry called supersymmetry looked promising. In a world where every particle has a partner of a different spin, contributions to vacuum energy can come with positive and negative signs that cancel more neatly. But supersymmetry, if it exists at all, has to be broken, because we do not see partner particles at the same masses as the ones we know. Once you break the symmetry, the cancellations stop being perfect, and the vacuum energy creeps back in. You can try to arrange the breaking so that the leftover is small, but so far no simple model naturally lands on the incredibly tiny value that dark energy seems to have. It feels like tuning an old radio and somehow landing exactly on one particular song among cosmic static. Another idea is that quantum field theory, as we currently use it, is simply the wrong tool to compute vacuum energy in a universe with gravity. Maybe the calculation we're doing is like asking how much weight a cloud has using the rules for a brick. Something about the way space-time and quantum fields interact at the deepest level might change the game. Perhaps a full theory of quantum gravity will reveal that what we call vacuum energy is not what we think, and that the cosmological constant emerges from some different kind of bookkeeping altogether. This is a hopeful path, but it is also a foggy one. We do not yet have a complete tested theory of quantum gravity. There are candidate frameworks, but none has marched through a clean list of predictions in the way general relativity did. So for now, saying that quantum gravity will fix the constant is more of a wish than an answer. Then there is the most unsettling possibility of all. Maybe there is no fundamental reason for the value. Maybe it just is what it is, and the only explanation we will ever have is that in most possible versions of a universe, the vacuum energy is too large or too negative for complex structures to form, so no observers arise to complain. In that view, we find ourselves in a rare patch of reality where the constant is small enough to allow galaxies and stars and life, because only such patches can host anyone asking questions. This is sometimes called an anthropic explanation, because it leans on the fact that we're here to observe anything at all. It feels unsatisfying to many physicists, because it swaps a mechanistic answer for a selection story. It also tends to pull our thinking towards speculative pictures where there are many universes with many different constants. Interesting, but hard to test. While these high-level debates play out, the raw tension remains. The cosmological constant, interpreted as vacuum energy, bridges the two most successful frameworks in physics, quantum field theory and general relativity. Yet it also highlights their deepest incompatibility. It sits at the junction where our best ideas refuse to agree. There is another puzzle layered on top, often called the coincidence problem. Right now, the energy density in dark energy is of the same order of magnitude as the energy density in matter. Not exactly equal, but comparable. That will not be true forever. As the universe expands, matter will keep thinning out, while the constant stays constant. In the far future, dark energy will utterly dominate. In the distant past, matter was overwhelmingly more important. So why do we live in this brief era when the two are similar? Why now in cosmic history does the cosmological constant become important at roughly the same time that complex structures have had enough time to form? Is that just luck? Is it another selection effect? Is it a sign that dark energy is not really constant at all, but a field that evolves in time in just the right way? Every route out of these questions demands something radical. A new symmetry that we have not yet seen. A new way to combine quantum theory and gravity. A new field rolling slowly through a vast energy landscape. Or a new willingness to accept that some numbers in nature might be environmental accidents, rather than deep necessities. Meanwhile, the observations keep sharpening. Better maps of the cosmic microwave background, more precise measurements of galaxy clustering, new catalogues of supernovae and gravitational lenses, all refining our estimate of how much dark energy there is and how it behaves. So far, the data keep pointing stubbornly toward a simple picture. Dark energy looks very much like a constant, with properties that match Einstein's term almost exactly. In other words, reality seems to be telling us that the maddening answer is also the right one. There is a tiny, persistent energy woven into the fabric of space. It is unbelievably small compared with the scales that quantum field theory lives on, yet large enough to steer the expansion of the universe. Our best calculations overshoot it by an absurd amount. Our best theories do not yet know how to back down. When physicists call this the worst prediction in their field, they are being more than dramatic. They are admitting that at the most basic level, we do not yet understand why there is something rather than nothing in the vacuum, and why that something has exactly the strength needed to control the fate of everything. In the next part, we will meet the competitors that line up next to the cosmological constant on the dark energy stage. Dynamic fields that slowly roll, theories that tweak gravity itself, and ideas that try to turn this crisis into an opportunity to probe new physics on the grandest possible canvas. When you hear the phrase cosmological constant, it sounds final. A constant is a constant. It does not change. It does not evolve. It just sits there, quietly reshaping the universe. For many cosmologists, that is both the appeal and the frustration of the idea. It fits the data with unnerving simplicity, but it also feels like an ending that arrives too early. So of course, physicists began to ask a mischievous question. What if dark energy is not actually constant at all? The first major alternative is something called a dynamic field, often grouped under the label quintessence. The idea is to treat dark energy not as a fixed property of empty space, but as a new kind of field that fills the universe, changing very slowly over time. Instead of a single number in Einstein's equations, you imagine something more like the inflaton field that might have driven the rapid expansion in the very early universe, but operating gently over billions of years. In this picture, the field has an energy density and a pressure that depend on how it moves through its potential landscape. That motion can make the effective dark energy density rise or fall, changing the rate of acceleration as the universe ages. If you describe dark energy by the ratio of its pressure to its density, the cosmological constant corresponds to a value of exactly -1. Quintessence in general gives you a value that can differ from that and can drift slowly in time. Why bother with this extra complexity? One reason is hope. A dynamic field might arise naturally in some deeper theory, perhaps linked to particles we have not discovered, or to the same ingredients that will eventually unify gravity with the quantum world. Another reason is the coincidence problem. If dark energy slowly evolves, you can imagine a history where its density just happens to cross the matter density around the present era, rather than sitting at a fixed value for all time. That is still a kind of coincidence, but one that might be easier to embed in a larger framework. Quintessence is only the first suspect. Other ideas push further. Some models propose fields whose pressure can be even more negative than in the cosmological constant case. These can lead to more dramatic acceleration, even to future scenarios where expansion becomes so violent that it eventually tears apart galaxies, stars, and eventually atoms. Such models are often grouped under labels like phantom energy. They sound exotic because they are. They tend to raise serious questions about stability and consistency, but they remind us that negative pressure is a wide playground, not a single point. There are also approaches that keep the idea of a smooth energy, but tie it more directly to the behavior of matter or to the geometry of space-time. In these theories, what looks like dark energy from the point of view of cosmic expansion might be a kind of effective description of more complex gravitational physics underneath. That brings us to a different class of suspect entirely. Maybe dark energy is not a new substance at all. Maybe it is a sign that general relativity, for all its success, stops being accurate on the very largest scales. Modified gravity theories try to adjust the rules of space-time themselves, rather than adding new ingredients to the cosmic soup. Some tweak the Einstein equations by allowing extra functions of curvature. Others introduce new fields that couple to gravity in non-trivial ways. A few imagine that our familiar universe is like a surface, a brain, embedded in a larger dimensional space, with gravity leaking into those extra dimensions at huge distances. In these setups, what we interpret as acceleration driven by a uniform energy might instead be a reflection of how gravity weakens or changes shape across cosmic scales. Light and matter still follow the curves of space-time, but the way those curves respond to mass and energy is no longer exactly what Einstein wrote down. Instead of a cosmological constant term, you have a modified gravitational law that quietly imitates dark energy. There is a tempting symmetry here. In the 19th century, when Mercury's orbit refused to match Newton's predictions perfectly, you could have added unseen matter to fix the discrepancy. People went looking for a new planet called Vulcan. It did not exist. The real answer was that Newton's gravity was only an approximation, and that general relativity would replace it. Today, we see galaxies rotate too fast and cosmic structures behave strangely, and we introduce dark matter. We see acceleration, and we introduce dark energy. Some physicists wonder whether, once again, we are piling on invisible substances to patch a theory that needs a deeper rewrite. The good news is that these alternatives are not just storytelling. They make different predictions, and those predictions can be tested. If dark energy is a cosmological constant, then the ratio of its pressure to its density should stay exactly at -1, and the way structures grow over time should follow a precise pattern that general relativity lays out. If instead dark energy is a dynamic field, that ratio might deviate slightly from -1 and might change as the universe ages. The growth of galaxies and clusters would be slowed or sped up in a slightly different way. Modified gravity theories can also leave fingerprints. They may change the relation between how matter clumps and how light bends, which shows up in gravitational lensing. They can alter the rate at which cosmic structures develop, even if the expansion history is tuned to look similar. Some can affect the speed at which gravitational waves travel over cosmic distances, something that can be tested when we observe both light and gravitational waves from the same cosmic event. This is where the universe becomes a laboratory for ideas that no particle accelerator can reach. By watching how galaxies cluster, how voids open, how the cosmic microwave background photons are tugged and stretched as they cross billions of light years, we can distinguish between a simple constant and more exotic alternatives. So far, the data keep leaning toward the boring answer. When we combine supernova measurements, galaxy surveys, lensing maps, and the microwave background, the effective dark energy looks very close to constant, with a pressure-to-density ratio near -1 and no strong evidence of change over time. General relativity also continues to pass every test we can perform on it, from the scale of solar systems to the dance of binary pulsars and the chirps of merging black holes. Yet the door is not closed. The uncertainties are still wide enough to leave room for small deviations, and small deviations can be big clues. That is why entire future missions and observatories are being designed not just to measure dark energy better, but to separate these suspects cleanly. Is the universe being pushed by a constant vacuum energy? Is it being steered by a slow rolling field? Or is gravity itself bending the rules? Underneath the technical details is a deeper philosophical tension. Each option carries a different vision of what kind of thing a universe is. A constant suggests a fixed background fact of reality, a number you just accept. A dynamic field suggests a universe in motion even in its emptiest corners, with fields drifting through vast potential landscapes. Modified gravity suggests that our most trusted description of space-time is an approximation of something stranger. The stakes are not just academic. Which of these stories turns out to be true will decide not only what equations we write, but how the future of everything unfolds. A constant dark energy leads to one kind of ending. A changing field leads to another. Modified gravity opens yet more possibilities, some gentler, some catastrophic. In the next part, we will follow those possibilities all the way to their logical conclusions, tracing how each vision of dark energy paints a different picture of the cosmic endgame, from slow fading to violent rupture to sudden invisible reset. When we talk about dark energy, it is easy to get lost in symbols and graphs and forget what is really at stake. This is not just an argument about a term in an equation, it is a debate about how the story ends, not just for galaxies, but for every atom that will ever exist. Once you accept that the universe is expanding, and once you accept that something is driving that expansion in a particular way, the future stops being an open canvas. It narrows to a handful of stark possibilities. The first future is the quiet one, the long, slow fade that people call heat death. In this scenario, dark energy behaves like a cosmological constant and keeps the expansion accelerating at a steady rate. Galaxies drift farther and farther apart. Over unimaginable stretches of time, star formation slows as gas is used up. Existing stars burn out. The night sky, already dark between galaxies, grows darker still as more structures slip permanently beyond each other's horizons. Inside galaxies, life continues for a while. New stars can still ignite from leftover gas. Planets can still orbit. But the supply is not infinite. Trillions of years from now, most stars will be dim embers, white dwarfs and neutron stars slowly cooling. Black holes will wander the cold, thin remains of clusters. Eventually, even those black holes may evaporate through quantum processes, leaking their mass back into radiation. What is left is a vast, almost uniform bath of very low energy particles and stretched out photons. No temperature differences, no free energy to drive interesting processes. A universe that has reached thermal equilibrium on a cosmic scale. It is not a dramatic ending. There is no final bang or crunch, just a thinning out of possibilities until nothing much happens anywhere. A cosmic retirement that never ends. The second future is not so gentle. Imagine that dark energy is not exactly constant but grows stronger over time. Its negative pressure increases. The acceleration of the universe speeds up more and more. At first, the effects look similar to the constant case. Distant galaxies race away faster. Empty space stretches more aggressively between clusters. But as the strength rises, the tug of gravity that holds structures together begins to lose. In this picture, often called a big rip, there comes a time when galaxy clusters are pulled apart. Later, individual galaxies are torn from their neighbours. Then, on a smaller scale, the pull that keeps stars in orbit around the centres of their galaxies is overwhelmed. Solar systems can be unbound, planets can be stripped from stars. If the trend continues far enough, even the electromagnetic forces that bind atoms together can be defeated. Molecules, atoms, even nuclei could be torn apart as space itself stretches faster than any binding process can react. The timeline for such an ending, if it were our fate, would depend on how quickly dark energy strengthens. It could be trillions of years away, or, in the most extreme versions, much sooner in cosmic terms. Either way, it is a violent contrast to heat death. Not a quiet fade, but a final shredding of all structure. The third future is less about being pulled apart and more about being rewired without warning. It comes from quantum field theory and goes by the name vacuum decay. The idea is that what we call the vacuum today might not be the absolute lowest energy state of the fields that fill space. It could be a false vacuum, a local minimum in a complicated energy landscape. If so, there is a non-zero chance that somewhere at some time the fields could tunnel into a lower energy configuration. If that happens, a tiny bubble of true vacuum would form. The boundary of that bubble would expand at nearly the speed of light, converting the old vacuum into the new one as it goes. Inside the bubble, the values of fundamental quantities could change. Particle masses, interaction strengths, even the dimensionality of space could be different. Chemistry, as we know it, might become impossible. Every structure, every star and planet and atom would be rewritten by new rules in an instant. The unsettling part is that there would be no warning. Because the bubble edge moves at light speed, nothing inside its future path would see it coming. One moment, the universe would be as it is now. The next, the laws of physics would be replaced. From a human perspective, there is no way to prepare. Either it never happens, or when it happens, it simply happens. The fourth future is the one we thought we were debating before dark energy crashed the party. It involves gravity eventually winning. In models where the total energy density of the universe is high enough and dark energy either does not exist or turns negative, expansion can slow, halt, and reverse. Galaxies that once fled from each other begin to fall back together. Temperature rises as matter and radiation are compressed. Over time, the universe could collapse into a hot, dense state, a big crunch that mirrors the conditions of the early universe in reverse. With a positive cosmological constant that looks truly constant, this big crunch option fades into the background. Acceleration makes it hard for gravity to claw things back. Yet if dark energy is dynamic, or if gravity changes its behavior at huge scales, it is not completely ruled out. It lingers as a reminder that our picture of the future hangs entirely on which of our ideas about dark energy and gravity turns out to be right. From far enough away, these four futures are variations on a theme. In every case, the universe we know is temporary. Structures form, live, and die. The difference lies in how gentle or abrupt the ending is, and in whether the laws themselves stay fixed or slide into something new. There is a strange emotional twist here. The version that is easiest to calculate, the constant dark energy that leads to heat death, is in some ways the most merciful. It gives the universe an almost unimaginably long time to do everything it can do. Stars can burn, planets can orbit. Life, in principle, can arise and think and build and wonder across vast epochs, limited mainly by local resources and creativity. The other futures shorten or sharpen the ending, making it violent or sudden or both. Yet even the gentle ending has a sting. It implies that there is a horizon beyond which we can never see or influence anything. As acceleration continues, more and more galaxies slip permanently beyond our cosmic horizon. Their light redshifts into invisibility. In the far future, observers in any one gravitationally bound region might look out and see only their own island surrounded by darkness. The evidence for the wider universe would fade. All of these scenarios turn dark energy from an abstract parameter into a storyteller. Its nature decides whether the cosmos coasts into quiet oblivion, rips itself apart, recollapses into fire, or snaps into a new phase without warning. For us, living in a thin sliver of cosmic time, the question is not just academic. It shapes how we think about meaning on scales far beyond human history. We do not get to vote on which ending we prefer. What we can do is measure. We can watch the expansion with increasingly sharp instruments, map the growth of structure, listen to gravitational waves, and test general relativity wherever it touches observation. Each new dataset is a clue about which path the universe has chosen. In the final part, we'll step back from the equations and ask what this whole saga really tells us about our relationship with the universe, about the power and limits of mathematics, about the way mistakes can become doors, and about how to live in a cosmos whose ending we may glimpse but never control. If there is one lesson the story of the cosmological constant keeps throwing in our faces, it is this. The universe does not care what feels reasonable. Over and over, our intuitions about what should be true have been quietly defeated by a few lines of mathematics that happen to describe reality better than our gut. The strange part is that those lines are written by us. We invent the symbols, we arrange the rules, then somehow the equations go out and predict things that nobody expected, and those things actually show up in the sky. It is tempting to treat this as magic. It is not. It is a very specific kind of honesty. Mathematics is ruthless about consistency. Once you set up a few basic principles and agree to follow the rules, you lose the freedom to cheat. You cannot decide that something is true on Monday and false on Tuesday because it feels nicer. The equations tell you what follows, whether or not you like the answer. That is exactly what happened when Einstein pointed general relativity at the universe. The theory said a static cosmos filled with matter is unstable. Einstein did not like that answer. He tried to bend the equations back toward his preferred picture by adding the cosmological constant. For decades, that looked like a cautionary tale about trusting math too little. Yet when the supernova data came in, the same constant reappeared as the simplest way to describe acceleration. Now the story's more subtle. In the first act, intuition overruled equations and got corrected by observation. In the second act, equations quietly kept a door open for a term that observation would later demand. The same symbol plays both villain and hero. This is not the only time mathematics has outrun common sense in physics. When the planet Uranus did not quite follow Newtonian predictions, astronomers used the equations to infer that there must be another planet perturbing its orbit. They wrote down where that invisible object should be, and then went and found Neptune almost exactly there. When Mercury's orbit behaved strangely, you could have invented another unseen planet again. Instead, general relativity changed the rules of gravity and the anomaly vanished. When Maxwell unified electricity and magnetism, his equations quietly implied that there should be waves of electromagnetic energy moving at a specific speed. Later, people realized that speed matched the measured speed of light. Light had become a prediction of math. Closer to our era, the equations of particle physics insisted that there ought to be a particular field that gives mass to some particles while leaving others massless. Long before anyone saw its signature, theorists could write down the necessary properties of this Higgs field. Decades later, experiments at a giant collider found a new particle with exactly the expected mass range and behavior. Again, a symbol on paper turned into a bump in the data. Cosmology has its own version of this pattern. The equation said an expanding universe should once have been hot and dense enough to glow with a thermal afterglow. Long before we built satellites to measure it, some physicists predicted that there should be a faint microwave background filling the sky. Later, engineers stumbled on that background as an annoying hiss in their radio antenna, and a new window on the early universe opened. In all these stories, the key is not that mathematics is smarter than humans. It is that once you commit to a set of principles and stop editing the consequences based on taste, the math will be more faithful to those principles than your intuition will. Intuition evolved to navigate food and danger, not curved space and vacuum energy. It is wonderful for throwing balls and reading faces. It is terrible at guessing what reality looks like far outside the human scale. The strange thing is that we keep forgetting this, even as evidence piles up. Einstein trusted equations enough to twist space and time, yet he still carried an emotional picture of a static universe that he could not quite let go. Many physicists trusted general relativity enough to drop the cosmological constant, yet were surprised when observations dragged it back. Even now, people argue fiercely about whether dark energy should be a constant or a field or a sign that gravity needs rewriting, and often the loudest arguments are about what feels natural. The universe has never signed a contract promising to feel natural. What it has done, repeatedly, is reward a particular style of thinking. You start with a small set of assumptions that are grounded in experiment. You write down the most general mathematical structure that honors those assumptions without contradiction. Then you follow that structure as far as it goes, even into regions that make your stomach flip. When you hit a prediction, you go and look. If the universe says yes, you keep the structure. If it says no, you cut it, even if it is beautiful. This process is not clean. It is carried out by humans with egos and blind spots and limited time. Mistakes are made, patches are added, fashions rise and fall. But over the long haul, the loop between mathematics and measurement has a kind of stubborn integrity. General relativity survived because it kept making correct predictions where Newton failed. The cosmological constant survived because the equations allowed it, and the data later demanded something very much like it. Quantum field theory survived because its absurd vacuum energy predictions do not show up in any experiment that does not involve gravity, and because its other predictions line up with particle colliders to ridiculous precision. When people say that mathematics is unreasonably effective in describing the physical world, they are pointing to this mystery. Why should symbols in our heads line up with galaxies and atoms? One possible answer is that we are not free to invent any math we like. We are shaped by the same universe we study. The patterns we find elegant may be the ones that reflect real regularities in nature. Another answer is that we forget all the failed formalisms that never matched experiment. History quietly filters out the useless equations. The cosmological constant sits at a particularly sharp edge of this mystery. On one hand, it is a triumph of the mathematical approach. A single term, allowed by the symmetries of general relativity, turns out to be exactly what is needed to describe a major feature of cosmic history. On the other hand, the value of that term is an insult to our deepest theories. The worst prediction in physics sits right beside one of the cleanest fits in cosmology. This is what makes the story of dark energy feel less like a solved puzzle and more like a doorway. The equations are telling us something we do not yet fully understand. They are whispering that our picture of vacuum, of space, of gravity is incomplete. At the same time, the match between theory with a constant and observation is too good to ignore. The right response is not to retreat into mysticism or give up on explanation. It is to recognize that we are in the middle of a conversation, not at the end. If there is a comfort to be taken from any of this, it is that mistakes are not dead ends in science. Einstein's cosmological constant, introduced for the wrong reason and rejected in regret, became the language of a later discovery. The wrong turn left a trail that future explorers could follow in a different direction. When you build your understanding on equations that tie tightly to experiment, even your errors can become landmarks. In the final part, we will look forward rather than backward. The next generation of telescopes and surveys will not just refine our numbers, they will stress test this uneasy marriage between mathematics and the universe on an even grander scale, and perhaps push us toward the next leap in understanding. Right now, as you listen to this, there are telescopes being built and detectors being cooled and mirrors being polished, all for one quiet purpose: to ask the universe again what dark energy really is, but this time with less room for it to dodge the question. Our current picture is already impressive, a working map of cosmic history from the hot beginning to the accelerating present. Yet the key ingredient in that story is still a symbol, a constant in an equation that we do not truly understand. The next generation of instruments is our way of saying to reality, "We heard your first answer, now say it again slowly." One of the sharpest tools will be an entire class of wide-field surveys. Instead of staring deeply at one tiny patch of sky, these projects will sweep across huge areas, mapping the positions and shapes of billions of galaxies. From those maps, we can read how structure has grown over time, how clumps of matter have tugged on one another, while expansion stretched the space between them. Tiny statistical patterns in the way galaxies cluster act like fingerprints of the underlying physics. If dark energy is truly constant, those fingerprints must follow a specific pattern. If it is changing, even slowly, the pattern shifts. Another powerful approach is to use the universe itself as a giant lens. Massive structures like clusters of galaxies bend the paths of light that pass near them. This gravitational lensing subtly distorts the shapes of background galaxies. By measuring those distortions across the sky, we can reconstruct how mass is spread out, including the invisible dark matter and how that distribution has evolved. Since dark energy affects not only how fast space expands, but also how easily structures grow, lensing becomes a way to test both sides at once. Geometry and growth woven together. Space-based observatories add a different angle. Telescopes above Earth's atmosphere can measure the faint glow of the cosmic microwave background with exquisite precision, and can watch distant supernovae without the blurring and absorption of air. Future missions are planned to measure thousands of Type Ia supernovae, stretching the distance ladder deeper into time. With larger samples and better control of dust and selection effects, we can refine the curve that first revealed acceleration and look for any subtle bending that might betray evolving dark energy. On the ground, giant mirrors will join the effort. Facilities like the upcoming survey telescopes will photograph the sky over and over, night after night, creating a movie of the universe instead of a snapshot. They will catch new supernovae in real time, track variable stars, and map moving objects in our own solar system as a bonus. In their data streams, hidden among transient flashes and slow drifts, will be the signals we need to tighten our grasp on cosmic expansion. Then, there is a newer messenger: gravitational waves, ripples in space-time from colliding black holes and neutron stars. Each such event can act as a kind of standard siren. The shape of the wave tells us how strong the event was intrinsically. Comparing that to how loud it appears lets us infer distance, just as we do with standard candles but without light. If we can also identify the host galaxy and measure its redshift, every merger becomes a new point on the distance map. These sirens are sensitive to different systematics than light-based methods, which makes them perfect cross-checks. All these observations feed into a common goal: to measure, as cleanly as possible, how the expansion rate changes with time, how structures grow, and how gravity behaves on the larger scales. From that, we can extract an effective pressure-to-density ratio for dark energy, and see whether it clings to -1 or wanders. We can test whether general relativity still holds at cosmic distances, or whether the data gently push us toward a modified law. It is entirely possible that after decades of effort, the answer will be that the cosmological constant really is constant. That dark energy is, to the limits of our measurement, a simple vacuum energy with a fixed density. In that case, the drama shifts from discovering new behavior to understanding why this particular constant exists and why it has this particular value. The crisis then belongs more to fundamental theory than to observation. The universe will have spoken clearly. The burden of explanation will fall on our deepest models of quantum fields and gravity. It is also possible that the data will reveal a small but unmistakable deviation. Perhaps the acceleration is easing or quickening in a way that a pure constant cannot quite match. Perhaps the growth of structure is off by just enough that we are forced to admit a new field or a tweak to gravity. Tiny departures can have huge implications. A slight tilt in the numbers might tell us that dark energy is slowly rolling down a potential, or that space-time itself flexes differently than Einstein thought when you zoom out far enough. Either way, the process will not be a single eureka moment. It will be a long conversation between theory and observation, fought in error bars and cross-checks and arguments over calibration. That may sound unromantic, but it is exactly that slow, collective stubbornness that has carried us from a static Milky Way universe to a measured, accelerating cosmos ruled by something we barely understand. There is another layer to this story that is easy to miss. For almost all of human history, the large-scale universe was a backdrop, an unreachable ceiling full of lights. Now, in the brief slice of time that our species occupies, we have instruments capable of measuring the acceleration of the cosmos itself. We are alive at the moment when the universe has grown old enough for dark energy to dominate, but not so old that distant galaxies have slipped forever beyond our view. We can still see the evidence written across the sky. That is an accident of timing so wild it is hard not to feel some awe. Einstein could not have predicted this. He wrote down a constant to hold a static universe in place, then threw it away when expansion was discovered. He did not know that 100 years later people would be pointing space telescopes and radio arrays and gravitational wave detectors at the sky, using that same constant as a starting point for new questions. His so-called blunder has become a compass needle in our exploration of reality. So where does that leave us, as small minds in a vast, accelerating universe? It leaves us in the middle of the best kind of mystery. One where enough is known to guide us, but not enough to close the book. One where equations and observations disagree just loudly enough to force us forward. Dark energy may turn out to be a constant, a field, a sign of new gravity, or something we have not imagined yet. Whatever it is, the act of chasing it is already reshaping our understanding of space, time, and nothingness itself. In the end, the cosmological constant story is less about a symbol in an equation, and more about a way of thinking. It shows that the universe can turn our mistakes into stepping stones, that mathematics can both reveal and conceal, and that reality is under no obligation to match our intuition. What we do have is the ability to notice when the sky fails to fit our expectations, to write new stories in the language of math, and to build machines that listen carefully to what the cosmos says back. As long as we keep doing that, the accelerating universe is not just rushing away from us. It is also pulling us toward deeper understanding, inviting us to follow its expansion not only in distance but in thought,